Welcome to a lesson with Dr. Powell. Let's take a look at an example of finding eigenspaces and eigenvectors for a matrix here. So we're going to consider this matrix. We can compute its characteristic polynomial by a determinant. Right? So this is just x minus um, the matrix. So x down the diagonal, like xi minus a, where this is a. Take a look at this. We find its determinant. We use a cofactor expansion, x times the determinant of this part. And then we change the sign here, plus 1 times the determinant of what's kitty corner. And we end up getting this, which factors nicely. Okay, so the minimal polynomial is going to be a factor of this. It could be this or this. Okay, let's take a look at this. Notice that if we do x plus 2 times x minus 1, we actually don't get the 0, which means the minimal polynomial actually is this itself. So we know that the range of x plus 2 is going to be the minimal polynomial of the range of x plus 2 is going to be a subspace whose minimal polynomial is x minus 1 squared. The range of x minus 1 squared is going to be a subspace whose minimal polynomial is x plus 2. Okay, so in particular, if we compute the range, the minimal polynomial on this is x minus 1 quantity squared. How did we compute the range of x plus 2? We simply just add 2 to this matrix here. 2's down the diagonal to get that. And then we can do, if we want to, we want to know like what's the dimension of the columns here. These columns span what kind of dimension. We could do a little we could do a row operation until we can identify where the pivots are going to be when we finish out reduced row echelon form, which we don't need to. We just need to identify where the pivots are. And that brings us back to tell us that these two guys will span the columns, and that represents a basis for the column space, which is the range of x plus 2. So this right here, the minimal polynomial is x minus 1 quantity squared. This is not an eigenspace, right? Because the minimal polynomial is not degree 1 right here. This is not an eigenspace. You could call it a generalized eigenspace if you really want to. But, I mean, you can call it that. But for us, we're just looking at just simple eigenspaces. So this is not an eigenspace. Okay, but we do know its minimal polynomial is x minus 1 quantity squared. All right, let's take a look and notice that actually the range of this, though, actually is the eigenspace for x equals 1. Why? Because what do we have to multiply this by to get to the minimal polynomial? X minus 1. Okay, so that actually gives us the eigenspace right here. X minus 1 finishes us off. So this is our eigenspace for the eigenvalue of x equals 1. We got that. All right. So now we could have also looked at the kernel of x minus 1 to get that. We subtract 1 from the matrix. We do a few row operations to get down to the reduced row echelon form. We use a little technique right here to get to the basis for the kernel. We look at the one non-pivot column, and for each pivot, we kind of go over. And since this is in column 1, we keep this in row 1, but we change its sign. Since this, going over here, this pivot came from column 2, so we keep this in row 2, we change its sign, and then we just kind of like adding ones down the diagonal, and there would be a 1 hitting there. This is the basis for the kernel, but that's exactly as we expected in our other calculation. Okay, so that's the eigenspace. Now, why don't we, okay, we can also compute the eigenspace for x equals -2, right? By looking at a kernel here as well, we can do a reduced row echelon form, find this, use that same technique to actually end up getting this as a basis for that eigenspace. And then we have our two eigenspaces, this guy and this guy. Here, we actually computed this by looking at the kernel of x plus 2 to do so. We could have also looked at the range of x minus 1 squared. Let's take a look at that. Actually, in computing this, notice, okay, this is all these columns are actually multiples of each other. If you just take the smallest multiple, that guy right there, that's exactly what we found, you notice, in finding the kernel. So there's more than one way to do it, either by a range or a kernel. Um, and we can get our eigenspaces associated with our eigenvalues. Thanks for watching.